This section is called Enthalpy Changes for Chemical Reactions, and by the end of this section you should have a good understanding and be able to use the enthalpy change for the conversion of reactants to products in their standard states. Some things to know about thermochemical equations. The sign of delta H indicates direction. The magnitude depends on the state of matter of reactants and products. The balanced equation represents moles of reactants and products. And the quantity of energy transferred is proportional to the quantity of reaction that occurs. Enthalpy changes accompany chemical reactions. For example, the standard reaction, delta H, so it's the change in enthalpy for the reaction, and then we have this little superscript 0, which stands for standard conditions, and we'll get to that in a second. For the decomposition of water vapor to hydrogen and oxygen at 25 degrees is plus 241.8 kilojoules per mole for the reaction. This is showing us that because it's positive, that it is an endothermic reaction. The decomposition of water, gaseous water, into gaseous hydrogen and oxygen is an endothermic process. So there's several important things to know about what this delta RH naught means. This designation of delta RH naught as a standard enthalpy change, where the superscript, that little 0, the degree sign, indicates standard conditions. That means that pure unmixed reactants in their standard states have formed pure unmixed products in their standard states. The standard state of an element or a compound is defined as the most stable form of the substance in the physical state that exists at a pressure of 1 bar and at a specified temperature. And for most sources, most temperatures, this is at 25 degrees Celsius or 298 Kelvin. The second thing to note is this per mole reaction. And this is the enthalpy change for a mole of reaction. And that's also abbreviated as RXN for reaction. And if you notice, if we look at this, we have 1 mole of water. Sure, we've learned before that if we have H2O decomposing into H2 and O2, we would, I'm going to cover that up here real quick, we would say, oh, we have 2 O's on the left, so we need 2 O's on the left, but that would give me 2 moles of reactant. And when we're looking at standard conditions, we want 1 mole of reactant. So it's okay to have fractions when we are doing this. Now, let's consider, so we just said that this reaction was an endothermic process. Our delta H was plus 241.8 kilojoules per mole for the reaction. So if we were to take this reaction and flip it, so my H2O that was a reactant is now going to be a product, and my 2 products are now going to be the 2 reactants. So if we look at the opposite reaction, the combination of hydrogen and oxygen forms 1 mole of water. Now the magnitude of the enthalpy change for this reaction is the same as that for the decomposition reaction, but the sign is reversed. So my sign, my delta H for the reaction at standard state was positive 241.8, but because I flipped my reaction, that means that I flip the sign, so it now becomes an exothermic reaction, so negative 241.8 kilojoules per mole for the reaction. Next, the value of our delta H depends on the chemical equation used. So let us write the equation for the formation of water again, but without a fractional coefficient for O2. So let's try this. So I get rid of that fraction. So that means I had to, in order to go from 1/2 to 1, I had to double it. To go from 1 to 2, I had to double it. To go from 1 mole of H2O to 2, I doubled it. We're still all balanced. But if I do that, my enthalpy also doubles. So I take my negative 241.8 and I times it by 2. So my enthalpy for this reaction is negative 483.6. So it is important to look at the chemical equation as it's written And then we can manipulate and figure out the enthalpy change if our reaction is flipped. So instead of a decomposition of water, if it's creating water. And then also with that, if I double or triple or quadruple the quantity, I do the same for my delta H. Now it's also important to make sure that the states of matter are identified. Because, for example, if we had hydrogen gas plus half of oxygen gas, and they create liquid water. Gas, gas, but it was creating water vapor. My delta H in this case is negative 285.8 kilojoules per mole for the reaction. And so if you look at that, it is greater than this one, right? This is the same reaction. I have a half of an oxygen plus H2 to create H2O. The only difference is that this is creating gas. It has a negative 241.8. This one's creating liquid, negative 285. So there is a greater exothermic reaction, and that only difference is the state of my product. So a few important things to note here. We know that our delta H has a negative value for exothermic reactions and a positive value for endothermic reactions. Our values for delta H are numerically the same but opposite in sign for chemical reactions that are the reverse of each other. Now, standard reaction enthalpies can be used to calculate the energy transferred as heat under conditions of constant pressure for any given mass of a reactant or product. So let's suppose you want to know the energy transferred to the surroundings as heat. If 454 grams of propane is burned at a constant pressure, given the equation for the exothermic combustion and the enthalpy change of this reaction. If we're given, and we know that propane, 1 mole of propane plus 5 moles of oxygen create 3 moles of CO2 and 4 moles of H2O. This is a balanced chemical reaction. And we're told that the enthalpy for this reaction is exothermic. We know that because of this negative sign. And it produces 2,220 kilojoules per mole. So let's say that I don't start with 1 mole. Let's say that I start with 454 grams of propane. Well, we know from our chemistry, if we have grams, we got to get to moles. So we're going to add up 3 carbons plus 8 hydrogens, and we're going to find that the molar mass of this compound is 44.10 grams of C3H8 for 1 mole of propane. We're going to take this one step further, and we're going to look at our mole ratios. And we've done this. We just finished with stoichiometry. So we can see that 1 mole of propane would be equivalent to 5 moles of oxygen, 1 mole of propane to 3 moles of CO2, 1 to 4 moles. But we don't want to know that. We want to know how much energy is transferred if I have 454 grams. So I want to get to energy. So what's great about given this enthalpy is we know that for 1 mole of propane, this much energy is released. So we can just use this ratio, 1 mole of C3H8, and again, I have to have that diagonally, is equivalent to negative 2220 kilojoules. Because look, this is kilojoules per mole. So this is kilojoules per mole. And we have grams, grams cancel, moles, moles cancel. I'm going to be left with kilojoules. So let's plug and chug here. So I've got 454 times negative 2220 and divided by the molar mass, 44.1. And I get negative 22854.4 kilojoules for my delta H. And we probably should look at significant figures. We started with 3 significant figures, so I'm ending with 3. 1, 2, 3, that 8 is going to make that a 9, so negative 22900 kilojoules. Now, if, let's say I started with 454 grams of oxygen, so I would do the same thing. I would go grams of oxygen to moles of oxygen for 1 mole of oxygen.
But this ratio would just be a little bit different. I would say that 5 moles of oxygen was equivalent to that same amount of energy. Or if it was CO2, my ratio would be 3 moles of CO2 for 2,220 kilojoules. So let's do another example just to kind of bring this home. We have sucrose, which is table sugar, C12H22O11. It can be oxidized to carbon dioxide and water by the following. So we're burning it, right? This is a hydrocarbon plus oxygen, creates CO2 and H2O. And we're told that when obviously we're burning, that's a negative enthalpy, telling me it's an exothermic reaction. So what if I had 5 grams? I don't have 1 mole of sucrose. I have 5 grams of sucrose. So I'm just going to figure this out, and I need to figure out what 12 carbons, 22 H's, and 11 oxygens molar masses. And double check my math, but I'm pretty sure it was 342.3 grams of C12H22O11 for 1 mole of C12H22O11. All right, so that's good. We went from grams to moles. Now I want to go from moles to energy. We want to figure out how much energy is produced if I just have 1 mole. Well, here I've got a 1 mole ratio, so I'm just going to say 1 mole of C12H22O11 creates negative 5,645 kilojoules of heat or of energy. So now we're just going to plug this in. 5 times negative 5,645 divided by 342.3. And we should get negative 82.5 kilojoules of heat. And I went to 3 sigs just because I was lazy and whoops, when I started this problem out, should have been 5.00. So sorry, 3 sig figs there, 3 sig figs at the end. Let's look at another example problem. Here we're told the combustion of ethane has an enthalpy change of negative 2,857.3 kilojoules for this reaction that is written. Again, these enthalpies are given to you. You don't have to just know that. So these are always given. But we want to calculate the delta H for the combustion of 15.0 grams of, what do we have, ethane. 15.0 grams of C2H6. So our first step is going to go grams to moles. And we know that there's when we're finding the molar mass, it's always for 1 mole of ethane. So let's do that quick calculation here. And I just added 2 C's and 6 H's to get a molar mass of 30.07. All right, that's grams to moles. And then, look at this one. We have another 1 mole of ethane, C2H6, for negative 2,857.3 kilojoules. So now we're just going to plug in our 15 times negative 2,857.3, all divided by the molar mass of 30.7 to get, I did something wrong. Did I not balance this right? You guys, I didn't balance this right. Because look, I only have I have 4 carbons on the right and I only have 2 carbons on the left. Ooh, that would make a big difference. I thought something didn't look right. Okay, well, hey, this is the beauty of checking our work. Something did not seem right. So I went grams to moles, but I need 2 moles of ethane. 2 moles of ethane creates this much energy. Okay, let's try that again. That makes sense now. That also gives me 12 hydrogens on the left and 12 hydrogens on the right. Okay, here we go. 15.0 times negative 2,857.3 divided by 30.07 times 2. So I'm going to do 30.07 times 2 in parentheses. And I should get, and I want 3 sig figs, negative 713 kilojoules. Okay, so this was grams to moles. For every 2 moles of ethane, this is how much energy is produced. Good work. Hopefully you're feeling good about this. We're going to do a little bit of practice writing thermochemical equations. So I want you to try to practice to write the thermochemical equation for the following. Knowing that 1 mole of nitrogen gas plus 3 moles of hydrogen gas react and create 2 moles of ammonia gas. And the enthalpy for this reaction is negative 92.22 kilojoules. So what would this equation look like if we had 1 mole of ammonia produced? What would it look like if we had 4 moles of ammonia that were decomposing? And what would it look like if we had the combination of 1 mole of H2 with the correct stoichiometric quantity of nitrogen? So why don't you take a second and see what that would look like and what it would do to the resulting H. Okay, so let's see how you did. The first one wanted the formation of 1 mole of NH3. So to form 1 mole, that means that I need to divide everything by 2, right? To go from 2 to 1. So I'm going to have 1 NH3. So divide, I'm just going to write over here, divide by 2. So that means I would have half of N2 plus 1.5, or we could say 3 halves, either one of these, of H2 to create 1 mole of NH3. That would also mean that I need to divide my H by 2. So this thermochemical equation would be half of N2 plus 1.5 or 3 halves of H2 to create 1 mole of NH3. And that would be negative 92.22 divided by 2 to give me a delta H of negative 46.11 kilojoules. Okay, that's for number 1. Number 2, I need to decompose 4 moles of NH3. So if I'm going to decompose, I have to flip this equation. So I need to flip. And in order to have 4 moles, I need to double. So I need to flip and times 2. Right? So that means I need to flip this sign of this and times it by 2. So I would go from a negative 92.22 to a positive 92.22 and times it by 2. So my delta H, before I even write it all, is 184.44 kilojoules. Now let's flip this. So I've got 4 NH3 decomposing. We got to times this each by 2. So 2 N2 plus 6 H2. That should be my second thermochemical equation. And then my third, it says we want 1 mole of H2. So in order to get 1 mole of H2, I need to divide everything by 3, right? 3 divided by 3 would give me 1 mole of H2. So I'm just going to write divide by 3. So I would have 1/3 N2 plus 1 H2. And 2 divided by 3 would be 2/3 of NH3. And my delta H, again, I didn't flip anything. I'm leaving it just in the same setup, but I need to divide my H by 3. So let's do negative 92.22 divided by 3. So I got a delta H of negative 30.74 kilojoules. Let's do a little bit more practice. See if you can find this out. So if we know that this standard molar enthalpy of combustion for propane, given this equation, is, so the delta H is negative 2,044 kilojoules. What is the standard enthalpy if I have 3 moles of propane? Well, hopefully you went from 3 moles of propane, and then all I needed to do was, if I know 3 moles of the C3H8, we know that for every 1 mole of propane, I'm just going to write propane, PRO, which is the same as this, is negative 2044 kilojoules. So I just need to do 2044 times 3, and hopefully you got negative 6132. Let's try another. This one's a little bit trickier. We said that the combustion of ethanol, which is C2H5OH. So hopefully you remember that the combustion means that we're taking that plus oxygen to give me CO2 and H2O. So we would need to balance that. And it's telling me that my delta H for this reaction is negative 277.7 kilojoules per mole. We're given a starting point. We have 9.22 grams of ethanol. And we want to figure out how much energy as heat will be released. So I need to go grams of ethanol to moles of ethanol, and I need to know what that balanced equation is between ethanol and my delta H. Can you do that? So hopefully you found that this was actually a 1 to 3 to 2 to 3 ratio. So we need to go grams to moles. We had to find the molar mass, and then 1 mole of ethanol for this much energy. And hopefully you got 55.6 kilojoules. Here's another one I'd like for you to just verify that you can get this answer. If we take a gummy bear and we burn a gummy bear is sugar, C12H22O11, and burn it, we can see it's combusting with oxygen to make CO2 and H2O. We're given the delta H is negative 5,645. Let's say that I had a 3.05 gram gummy bear. See if you can get the enthalpy of this, the amount of heat or energy given off. See if you also get 50 kilojoules.